start, it's a real pleasure to introduce our seminar speaker for today. I think for most of you, he doesn't need an introduction. Dr. Ed Lewis is Vice Chair, Professor and Vice Chair in the Department of Entomology and Nematology. I think many of you know he's also Editor-in-Chief of the Journal of Biological Control. I'll give a little bit of Ed's background. I think some details are very interesting. It's a very diverse background as well. So Ed is from Central New York State, and then went to Cornell University, received a BS degree in Conservation of Natural Resources. So after receiving his BS degree, he worked as a research technician dealing with mice and vole control in apple orchards in Hudson Valley of New York. And then he also sort of paid his own way by being a carpenter, by being a house painter, and by being a short order cook. And so those three things obviously can serve him well if things don't work out for him here. Okay, so from New York State, he went down to, let's see, Missouri, or University of Missouri, where he got a master's degree working on the migration of black cupworms. And then from Missouri to Auburn University, where he received a PhD working on sort of the ecology and species interactions of bark beetles attacking southern pine trees. So you notice in that background, no nematology really, just sort of ecology, population dynamics. And it was at Auburn that he ran into Shirley Lockhart and basically his better half. And so from there, both Ed and Shirley, they sort of had a pattern where I think in some cases Ed followed Shirley, and in some cases Shirley followed Ed. So from Auburn, basically, they both went to Rutgers University, and that's where Ed, I think, started working with nematodes. He worked in the laboratory of Dr. Randy Gogler. And so from Rutgers down to Maryland, where he worked as a postdoc in Mike Raup's lab, working a little bit with nematodes, ornamental plant insects, and I think Shirley was at Walter Reed then as well. So from Maryland, then down to Virginia Tech, where Ed took a position as assistant professor in entomology. He had a three-way split, research, teaching, and extension, worked with nematodes, black vine weevil, turfgrass, things like that, and Shirley had an appointment in the Department of Biochemistry. And then things took a positive turn for both of them. Basically, they both headed out west. Shirley took a position in the medical school here, and we hired Ed basically as a split appointment between entomology and nematology, and obviously we've merged as a department, and now Ed is vice chair. So that's sort of a brief synopsis of Ed and Shirley's experience, and it's great to see a number of people here today, and Ed's going to talk about some aspect of sustainability, as you can see from the title. So let's welcome Ed.
Thanks, Mike. Thanks to all of you for coming. So today, I'm not going to talk about insects or nematodes. This will be another sort of departure, although I've never been afraid to jump into new things. So we'll see how this goes. But this is kind of an interesting relationship that's developed between my laboratory and a startup company that is located right now in West Sacramento. They have a pilot plant, and the startup company is called California Safe Soils. And they make a fertilizer product. And I'll tell you about how that's made and what it looks like and what it does, and then sort of the steps that you go through to get to the point where you can actually have a product that you sell. So we don't sell it, we only do the research part of it. But it actually has an interesting story that goes along with it. Now, many of us in the department work with industry one way or another. You test new materials, you help get products to market, but this is the first time I've ever been involved with actually getting a company from zero to existence before. So it's kind of a different relationship from any that I've had before. This is a picture of the pilot plant. It's over in West Sacramento, as I said, and the company itself started in Florida, but they ran into trouble in Florida for basically two reasons. They started it up in 1986, and then we know what happened in 1987 and 1988, so anything that you were doing that required money in those years kind of swirled down the drain slowly and was in trouble. The other problem that they didn't have was that they created a product. The product had, intuitive value. Everybody thinks, well, how could that stuff not work? However, they didn't have any research basis for the claims that they made, and that is a mistake that they tried to fix when they took the technology from Florida and brought it out here. So the story of how I got involved in this basically starts with these two brothers who have this technology and they wanted to start this company. One of them lives in San Diego. The other one lives in New Jersey. I'd say the San Diego guy won, but anyway. They were trying to figure out how to engage some researchers into testing these products, and the one brother in San Diego went to his state legislator and said, who in the UC can we approach to even see if we can talk about how to move forward. So the legislator went to an intern who was assigned to him to be sort of an in-between between science and this person, and this intern was Ken Spence, who was a member of this department, did his PhD with Jay, and then he came to my lab and did a postdoc for a couple of years. So there's some element of luck involved in being in the right place at the right time and having other people in the right place at the right time. But through Ken's introductions, we started this project about 2 years ago. So what I want to do today is sort of, with that short introduction to how it started, talk to you about the process that this company has developed to turn grocery store waste into an agricultural product, and talk about the first evaluations, some field trials, and where we're going from here. Okay, so first of all, though, let's think about the potential impact of a product like this. So the first thing to think about is that the average grocery store in the United States throws away 600 pounds of food every single day. Okay, that's a lot. That's a lot of stuff. And the stores actually have to pay a fee to get another company to haul this food away that has expired. It's past the sell-by date, so they can't sell it, and they can't even give it away because the liability that would be associated with it. If someone were to become infected with salmonella or something like that, the grocery store, they'd be liable for that. So they're reluctant to even give stuff away. So they have to pay to have this hauled to a landfill or a composting facility, and because of California legislation now, 50% of anything that they throw away has to go to a composting facility as opposed to a landfill. So there's a limited capacity there. And finally, if you talk about composting food into something that would be considered compost, something that you'd want to put out on a field, it takes anywhere from 6 months to a year or more to come up with a consistent product that anybody would want to put out on their field to improve organic matter and soil structure and things like that, for which compost is generally used. So you can see that there's an impact on waste management right off the bat. Okay, there's also a potential impact for farms. Okay, that is that, just to give you an example, if you go to a typical tomato production area around here, and we all see them, right? They're surrounding us. So the average grower puts between 125 and 250 pounds of nitrogen per acre per year. This is only nitrogen. That's not all the other stuff that goes on there, like phosphorus and potassium and micronutrients and things like this. This is only nitrogen. So this is a really high rate. It's expensive, and a lot of the nitrogen either percolates through the soil and ends up in groundwater, or it's eroded away and ends up in wastewater, and we know that that's a huge problem based on a study that came from UC Davis earlier this year. So if the material works, you could reduce NPK applications pretty significantly. And then I'll show you some data that supports this later. You can improve the content of soil organic matter really consistently. And increased soil organic matter, by and large, is agreed on to be a really good thing if you're trying to grow plants in soil. So here's this report that was put out by UC Davis scientists earlier this year. This is available online, and you can look at it. And if you really want to be scared about what you're drinking, you can have a look at this, because it's a very sobering kind of a report. Okay, so if we talk about a product, especially one like this, there are some problems that are associated with it, right? There's a little bit of skepticism, because there's about a zillion products out there that claim that if you put this on your soil, you're going to have pumpkins bigger than your house and zucchinis the size of Volkswagens and everything else. They don't always work. Sometimes you get freakish things like that, which I'm not sure that everybody would want to have anyway, but you can get some results. But a company like this that produces a new material faces a huge degree of skepticism, especially from commercial ag, because the people in commercial ag have been sold this stuff over and over and over and over, and the effects of it are oversold, and they're almost always disappointing. So you have to sort of overcome this hurdle, and the way to do that is to be really open with production and everything else, and very realistic in the expectations that you set on this. You can't say that you're going to get giant onions all the time when you grow it, but you might be able to say that for the same cost and for much less nutrient problems, you can get the same output that you did with your standard NPK fertilizing rates, and that's sort of the direction where we were going. Okay, so what is it? So this stuff is actually called food hydrolysate. Okay, so food hydrolysate basically means ground up and digested food that ends up looking sort of like milk, chocolate milk, and I'll show you a picture of it later. Not terribly appealing to look at, but anyway, so this is a promo slide from the company here. So basically what they're talking about is that you start in the supermarket and you collect the food, you process the food into this fertilizer, you take the hydrolysate, you give it back to the farmers who grow the food that goes to this. So you can see there's sort of a virtuous circle here, hopefully, where things improve better and better. And we'll talk about picking things up. So this is not, they don't like to, the company, and I agree with them, don't like to think of this as sort of waste management. It's sort of, you collect the food at a pre-waste state, right? This is not rotting food, okay? I mean, most of the stuff from the produce bin you could probably put back in the produce aisle and nobody would know the difference. It's all fresh, it's not starting to rot, anything like that. So they pick up every day using these refrigerated trucks. They take meat, fish, produce, and deli. Down here you can see these containers that they have. So in the meat department, they have a refrigerated container. In the produce and the deli, they have other ones, but basically they pick this stuff every day, bring it back to the plant to start the process where they make the hydrolysate. And then this is typically when you bring it back, this is the CEO right here, Dan Mora. He's the brother from New Jersey. You can tell by his pale complexion. And this is Mark Lejeune. He's the chief operating officer. And Mark is the person who actually makes all of this machinery run and comes up with all of the ideas for improvement and things like that. So this is what a collection from a store would look like. And so this is about a 3 foot by 4 foot by this deep tub. And you can see it's almost filled with these vegetables, and they look pretty good. I would probably eat those. And then the meat, I'm not sure I would eat that, but anyway, it's fairly fresh. And then this is what the inside of the pilot plant looks like. So you have a few different working parts here. The interesting thing, though, is that these are all existing technologies. And mostly for food processing. So it's not a really expensive undertaking to put one of these pilot plants together. Not that I'm suggesting anybody does that. I'm sure they have all kinds of patent protection. But so the food is brought here and it's put into this big hopper, which is a coarse grinder. So just right on the edge, you can see a forklift. So a forklift lifts up the buckets, tosses them into here where they get ground up, and then they go through this pipe, and the ground up stuff goes into here, and it dumps into this big sort of cauldron here. And this is actually called a ribbon blender. So inside that, they have sort of like a big auger that goes around and around, and it grinds up the food into very small pieces. Then they add an enzyme solution to digest it, and it's brought to basically body temperature, so it kind of works like our stomachs in here. And if you ever wanted to know what that looked like, you can sort of see the stomach. More grinding, there's the stuff. So this is after about 2 hours. So you can see this is, again, meat, deli, fish, and vegetables. And to maintain a consistent product, they put in the same proportions of meat to all of the other products. So they end up with something that comes out the same every time. So here it is grinding. A couple hours later, there's a heating step. So they actually pasteurize this stuff so there's no foodborne pathogens associated with it, which is necessary if you want to be classified as anything other than a renderer. Okay, and I don't know how many of you know what a renderer is, but basically it's somebody that takes animal carcasses and carves them up and, you know, uses all of the products that can possibly be used for pet food and stuff like that, and then throws the rest of the stuff away. The problem with being a renderer is in zoning regulations. So you have to be sort of out in the country, and nobody wants their house or store next to a renderer. So being not classified as one was an important step for these guys. So this is closer to what it looks like, but not quite. After this step, it's pasteurized. So it's further ground to less than 15 microns. So they use the same kind of a grinder that they use to make ketchup. As I said, this is food processing stuff. So they use this, it's an inline grinder, so the stuff is actually about the consistency of ketchup. At the end, they stabilize this with phosphoric acid down to this pH, 3.5, and I put a can of, or a bottle of Coke here because Coca-Cola is also stabilized with phosphoric acid down to a pH of about 3.5. So it's just like Coke. It's probably better for you than Coke. So in one run of this cycle, they make 200 gallons of the hydrolysate. And the hydrolysate is stored in 6,000 gallon holding tanks. And this also helps assure that the product is very consistent time after time. So you can imagine if you got, you know, 3 of those big cartons full of beets one day and end up with a big slug of iron, right? So you have to be able to blend that away so you end up with a product that's the same every time someone buys it. And they have that, and we've done some tests. This is what the material looks like. Remember, it's this color, about the consistency of ketchup. The particle size is low enough that it easily is applied through drip irrigation. That was one of the problems, one of the potential problems that we thought about early on, is that if this stuff, if it clogs up drip irrigation outfits, growers are going to be really mad for a really long time, and they're never going to buy this again. So we've tested and tested and tested that, and it actually flows through drippers really well, no problems. They also went through a microbiology test from the CDFA and have come out clean, so they're pathogen free. They're all ready to go here. Oh, H to H. The stuff is called harvest to harvest. that's the product name. I guess I haven't mentioned that. Okay, so where do we come in? So that's everything up till making the product, and our job in our lab is to figure out, well, what does it do? We want to answer some questions here. So you have to look at nutrient content. You have to make sure it's a consistent product, and we have to come up with application rates, which sounds easy at first, but it's really not when you talk about fertilizers, because it's not that you're just killing bugs out there. You have to come up with something that's going to improve yield, and it's still going to be economically feasible for growers. So this is actually a pretty tricky problem. The first question, of course, is does it work? And then the next question is, if it works, what does it do? And the order here is really important, because if it doesn't work, nobody's going to care what it does. So if you're working with a company that's developing a product like this, practicality just states that the first thing you have to really look at is the impact on yield and figure out, is anybody going to be interested in buying this? Because if they're not, then there might not be much reason to move further on. Okay, so if you look at the nutrient content, and before I talk too much about this, the way we figured out that we had a consistent product was that we took samples of 50 individual 200-gallon runs, and we kept those samples. We had those samples analyzed for all of these different nutrients, as well as things like heavy metals and stuff that we didn't want. And then we did a simulation to figure out how many of these batches would you have to mix together before you ended up with a product that adding one more batch to doesn't change it. It's called a Monte Carlo simulation, and it's an easy way to figure this out. And it comes out to basically, if you mix 5 or 6 of these batches together, you're pretty stable. So if you think about 6,000 gallons, so you're mixing 30 different individual runs together, so the product is going to be really stable. Now, one thing to think about here, so this is the NPK. So it's basically a 1-1 and almost 1. So when you buy fertilizer for your tomatoes and you have 9-9-9 or 10-10-10, okay, that's nitrogen, potassium, and phosphorus, or nitrogen, phosphorus, and potassium rather, NPK. So this is pretty low. There's a lot of other stuff in here, but the NPK is really pretty low. Okay, so figuring out application rates, as I said a little while ago, it's not as easy as you might think. So we did a few different things here. One, we just did a trial where we added really a lot of this, just to make sure that it did something, all right? Because we basically were starting from scratch. Now, when you think about what goes into the material, all right, you've got this material, it's all digested food, you have proteins and sugars and amino acids, and you think, well, shoot, it's got to at least be an okay fertilizer, which is sort of the way I was approaching it, but you also want to just make sure of that. After that, we did a dose response in the greenhouse, and we used tomatoes as a test plant. So the first thing that we did was tested it against urea, which is basically nitrogen. Urea is about 40% nitrogen or so when you put it on the soil. And you can see the plants over here. Here's the control and the H to H and the urea. So, here's the basically plant height. So we were just growing it out for about 4 weeks just to look at the plant responses. Plant responses looked pretty good. So it was worth going on and doing a more detailed kind of a trial where we could at least start to get a handle on how much of this stuff you need to put out into a field to actually grow plants. So we started with tomatoes again, transplanted them into 6-inch pots. We added 100 mils of liquid, which contained rates that were equivalent to 500, 1,000, 1,500, and so on per acre. Now, obviously, some of these rates are ridiculous because nobody's going to put 3,000 gallons of anything per acre on pretty much anything. But we measured plant height and stem width and stuff like that. And so when we got to the end, what you can see is that at 500 gallons an acre, the equivalent of 500 gallons an acre, you start to get a plant response here. And it's more when you add more, but you know, there's also some diminishing returns that you have to think about. And you also have to think about what's reasonable as far as what anyone would go. So we came up with a standard, and this is just a starting point of 500 gallons an acre as an application rate. Okay, and that was based partly on economics because it's going to be too expensive if it's very much more than that, and partly on efficacy because we did see a plant response to that level of application. So the next step was to do field trials. Now, as I said before, sometimes you have to do things in an order that you wouldn't normally take when you're, working with a product like this. And this addresses that idea of, does it work on a field scale, and is it going to be worth actually sort of digging deeper into the soil ecology to figure out what's going on here? So we did more than 30 different field trials across the state in all of these different commodities. So this was quite an undertaking. We meaning it's sort of the royal we of like everybody who was involved or could be cajoled or bribed into doing anything of this. The cajoling was my part. The bribery was on the company because they had the money. So anyway, we did all of these different trials throughout. Some of these are actually still going. Some of these trials we're going to be able to do a second year because the second year is going to be very interesting to figure out what's going on in the soil as opposed to 1 year of treatment. And then we developed some standard methods. And these have been adapted quite a lot over the course of the season, but we basically had 4 treatments that we wanted to compare with each other. We wanted to look at a control where no fertilizer was applied. Now, you wouldn't think that asking a tomato grower who has many thousands of acres of tomatoes to leave one row unfertilized would be that big a deal, but it's actually impossible to actually get anybody to do that. So, on some of these we actually had a control, but on many of them we didn't. Okay, so that would be a negative control. A positive control would actually be asking the grower to do what you usually do. Okay, whatever you did last year, do again this year, and that's the standard against which we will compare the results from the trials using H to H. Okay, so we had the H to H alone starting at 500 gallons an acre, but again, this was changed back and forth depending on a number of things, and I'll explain that in a minute. Now we had another one where we asked the grower to cut in half whatever they did last year and supplement with 250 gallons an acre of the H to H. So these 4 things that we wanted to compare. And then as far as timing and method and everything like that, we were very interested that the growers would do everything the way that they normally do everything. Okay, so if you're trying to develop a product or you're trying to introduce a biological control agent or any kind of a new practice in agriculture, you have to make it easy. Okay, you can't say you've got to change everything that you're doing to use this product. You have to make it easy for the product to be incorporated into the production schemes that are being used currently. So basically we said, whatever you do, just do it the same way. And then for data that we collected, mostly we collected yield data because this is sort of the bottom line for growers. If yield took a real hit, this probably wasn't going to go much further. unless you could sell it on the idea of reducing landfill use and things like that. It would still be a valuable product, even if it didn't really. I mean, it's better putting out this liquid on the soil than it is building mountains of you know, compost and landfill. So there's that to think about. But so we wanted yield data, and then we also collected some data on mostly soil organic matter. Okay, so when these were applied, they were applied either by drip irrigation, microjet, by hand, sometimes some other things. So, you know, whatever was standard practice. And then when we calculated the rates, we had 500 gallons for the season. Okay, so that doesn't mean all at once. So a lot of times, for instance, for typical tomato nitrogen timing, you have 200 pounds of an acre for the whole year, but half of that actually is applied before the tomatoes are transplanted into the field or as they're transplanted into the field. So half of it is right up front to bump the tomatoes and have them get started. And then there's usually one or two other subsequent applications based on reading the amount of nitrogen in the leaves and petioles and stuff like that. So it's not one application. So these application methods and rates are worked out really pretty well. Okay, another thing that I want to mention though is that 500 gallons per acre was what we calculated for those pots. So basically, you had a 6-inch pot, you scale it up to 43,560 square feet, which is an acre, and then you expand that. So, you know, it's not really exact. But what we wanted to do was to see if we could reduce that. So then we started calculating, okay, well, if you only irrigate with drippers, you're getting the material right to the root zone, and you're only really irrigating about, you know, a square foot, not all of it. So when you look at the area that is actually under, you know, receiving the fertilizer, 500 gallons an acre turns into about 75 gallons an acre, because you don't count the area, you know, between the rows, which is actually most of the area of the field. So you can see that here. So the drip line would be going, you know, right up the middle of that. Okay, and then you'd have water and fertilizer moving out, you know, maybe 8 inches on either side. So the fertilizer is actually being applied really efficiently to the root zone where the plant can use it. And this is just this is like a giant squash pitcher a little bit, but bear with me. So this is the H2H treatment here, and you can see the difference in canopy between, this is what the grower was using, and this is the H2H treatment. So you had a lot of vegetative growth here, which isn't necessarily what you want, because you don't eat tomato leaves, you eat tomatoes after all. But, you know, vegetative growth does indicate a pretty positive plant response. So when we looked at some of these data, this is just from one trial, and I'm purposefully not showing you the best trial. Okay, I'm showing you sort of an average trial. So what we did see is, you know, if you look at grams of tomato per plant, yeah, there's a little bit of a difference, but it wasn't significant. If you look at the number of tomatoes per plant, it's about the same. Interestingly, though, the bricks of sugar was increased in the H2H treatment. We haven't really figured out how that could possibly happen, but there it is. But what we did see, and there were 5 different trials in tomato across the state, and on average, the H2H treatment yield was between 10 and 14% above what the standard yield of whatever the grower was using before. So, you know, when you think about that on a scale of hundreds of acres, 14% more is pretty significant. And since the H2H product is going to be on a price point about the same as their regular fertilizer, this is pretty good news as far as tomatoes go. We looked at citrus also. I'm not going to spend too much time on this. This was done in Porterville on Washington Navels, and you see that the H to H it's about as good as whatever the grower was using. So the really surprising outcome that we had was actually with strawberries, and it was usually when you don't want to say words like incredible and unbelievable when you're giving a scientific presentation, but let's just say that I was very surprised by these results. So we did a trial. This is in San Luis Obispo, Santa Maria, and these are strawberries. This is basically how they're planted, and this was done actually several different times, but the data that I'll show you were collected by Surendra Dara, who's a farm advisor at San Luis Obispo County, and some of you may know him. So we had 1.2 acres for each treatment, 6 replications per treatment, and then again, the way this was applied was just following whatever the grower was doing. So it was either what the grower was using or a substitute for the product that we're trying to test. An interesting aside, when you ask the growers what they use, they really won't tell you because it's kind of, they're a little secretive with that kind of information because they have something that works and they're in a competitive business, so it makes sense. Okay, so these data were, as I said, really surprising. So the blue bars are actually the amount of culls. So a cull growing strawberries, they're either too small or they're too green or they're rotten or they get bashed up when they're getting picked or something like that. But they're the throwaways. So the red bars are what are really important. And if you look at this is total harvest through the whole season, but this is about a 35% increase. And with strawberries are a really, really high value crop. So if you can increase production by that much, that translates to a lot of money. And if they looked at the amount that the grower would actually net, okay, this is with the H to H treatment, and this is with what they were doing before. Obviously, these growers are pretty happy with this test. So basically, it's about $2,000 net more per acre. And if you think about selling this at a cost of maybe $300 an acre, that's pretty compelling information to these guys. Okay, so I said that we're also interested in what goes on in the soil. So, from my standpoint, the really interesting stuff is what happens when you put it on the soil, what happens to the soil itself. But again, you have to justify doing that research. So I'm just going to talk about one small series of tests that were done in an apple orchard. And this was done by Duarte and Associates, who are contracting with California Safe Soils to do some of this work. And what they did was they did a field trial in an almond orchard. And in addition to monitoring yield and everything like that, they looked at what happened to soil organic matter. And basically the important part is right here. So it was 0.8% before they started, and at the end of the season it was 1.2 almost. So a 44% increase. And these are small numbers, but this is actually pretty significant and really surprising also. That's a huge increase in soil organic matter, especially considering how much of the material was put on. So one of the questions that we have going ahead, and this isn't the only time this happened. This happened in a turfgrass trial, it happened in strawberries, it happened in this almond trial. So it seems to be pretty consistent. But a big question is how does this happen? How does that much organic matter increase occur after these applications? I don't have a good explanation for it yet. Hopefully next year I'll have a good explanation for it. So anyway, that is also really sort of positive. That's a very positive impact from this material, because increased organic matter has two big pluses when you think about California agriculture. The first one is that with increased organic matter, you have increased water holding capacity of soil. Water's really expensive and becoming more rare as we even sit here. So if you can increase that, that's a good thing. It also causes an increase in soil's ability to sort of hang on to nutrients and not let them leach out into groundwater, which is another positive aspect. So where do we want to go from here? So as I said, the first step was proof of concept. You have to show that the stuff works, otherwise the other stuff doesn't really matter. So we can start looking at more interesting questions now. So we want to look at nutrient leaching rates. So you can do this fairly easily, and you can measure the amount of nitrogen that moves through the soil column when you have treated and untreated soil, so we'll be able to get a handle on that. We want to look at water holding capacity. If soil organic matter is increased to that level, we should see a big increase in water holding capacity. We want to look at changes in soil organic matter and other kinds of structural things like aggregate size and things like that. We want to look at plant response in a little more detail. We want to, for one thing, look at the timing of plant response. How long after the material is applied do the plants begin to flush? We want to look at application of this in tandem with other kinds of products. So one of the things this material should be doing is increasing microbial populations in the soil. So there is a large and growing industry in the world making microbial products for addition to soil to increase productivity. And there's lots of different things, but for instance, you can buy mycorrhizal fungi, you can buy nitrogen-fixing bacteria, you can buy a whole slew of other things that are added to soil. And if those products work, and this product works, if you add them at the same time, you should get a big boost in those beneficial microbial populations. So we also want to look at that. And also, just because it works in one kind of soil doesn't mean it's going to work in another kind of soil. Even, just because it works right here doesn't even mean it's going to work over there. So again, this is something about managing expectations. You can't just sell something and say, no matter where you are, you can put this on the soil and it's going to work great. Because chances are it's not. It'll work better in some places than others. The more we know about how it works, what it does, and how long it lasts, the better we'll be at predicting success and failure based on physical, chemical, climatic conditions, what crop you're using, and things like that. So the whole the object of this is you want to develop this product, but you have to make it a consistent product that has predictable outcomes. And overselling is the death knell of all of these new kinds of products. You have to be very realistic with growers and tell them what it'll do, but make sure you really tell them what it won't do, because that's what they're really going to remember a lot of the time. So that's where we are. I'd be happy to answer any questions. Lots of people are involved in this. There's everybody in my lab, some visiting for a short time, some visiting for a longer time. And then the folks from California Safe Soils have been very generous with their support and their help. So I hope you have some questions. I'm happy to answer them.
I just had a question. So you said that you wanted the product to be consistent. So when you have a big shipment of something like these, do you have holding refrigeration things there, or do you just do you wait until the next day you'll mix them in with the next shipment, or?
Well, no, they don't. They process them right away, and so they don't want to hold on to it at all because the food begins to degrade pretty fast. So the fact that 30 batches are mixed together into one tank, it's sort of slugs of materials from one thing are kind of washed out. So One or two batches that are unusual don't really affect the whole thing. Yep.
You talk about applying 500 gallons per acre, but then you showed that the drip zone was small. So you're actually applying 75 gallons per acre? Or?
Yeah. So the strawberry data, that was 75 gallons an acre.
And it's at 75 gallons per acre that's equivalent to the cost of nitrogen fertilizer.
Yeah, yeah. So what the company's trying to do is actually develop some long-term agreements, because it's an interesting thing because of the business plan. So they collect the material from stores, but if they don't have a place for it to go right off the bat, you end up with an ocean of that brown stuff. So what they want to do is develop long-term contracts with grocery stores, and they've just developed one with Save Mart actually, and they're building a commercial sized plant in Roseville. They're starting right now. So then they've got to make sure that the pipeline is complete to go to these growers. So they're trying to develop contracts that'll say, okay, if you sign up for 5 years of this, you can get it for 250 gallons, or $250 an acre for this application rate. So, Steve.
My first thought when I saw that field in Santa Maria was how unblack the soil was, so low organic matter. So do you think the basal level of organic matter has something to do with the significance of the effect on the plants? So you have very little organic matter, you have this.
Well, possibly, but I don't know what it was before we started, so I can't really answer.
I actually have two questions. Was there any crops that you looked at that had no effect or a negative effect in comparison to what they normally use?
Nothing had a negative effect in all of the trials that we do. I don't think that any of them had this product doing significantly worse than what the growers were using.
Or were there any crops that had no effect, no noticeable effect? Like
You mean it was just sort of as good?
It was.
Well, most of the tree crops that we tested turned out to be not really very different, but that's not surprising because you've got a lot of history in a tree crop, so it takes 2 to 3 years of a change in management to actually have any effect on yield or anything like that. So like for citrus, it was kind of the same as whatever they were doing. Same for avocados, same for olives.
And my other question is that since the fruits and vegetables and meat you're starting with are not necessarily organic, would this ever be qualified for application to an organic situation?
So that's an interesting thing because the product as it is with phosphoric acid is not labelable as organic, not because of the food that goes into the product, but because phosphoric acid is the problem, even though that's kind of a natural product too, but I guess not natural enough to be organic. So the company actually has gotten a registration for an organic product in Washington, and they used lactic acid instead of phosphoric acid as a stabilizing agent, and that's all it took. It's not labeled in California yet, but it's sort of on the way, so they will have an organic product yet.
So is there any chance that the dramatic yield that you saw with the strawberry application was due to suppression of common soil-borne pathogens, especially verticillium?
It's possible. We didn't look at that, but just anecdotally, some other folks have seen a reduction in verticillium among other things in areas where it was applied. So maybe.
Yeah, I was just wondering, like the math that you said that they need 50% of their stuff to go to a landfill by like law or something.
Yeah.
Like even if they were mandated and subsidized to give 100% to your company, is just in California in general, do they throw enough tonnage away to fill the needs of most of the Central Valley?
The guys in the company did this application, and I want to say yes, by and large, because I forget how many thousands of tons of stuff is tossed daily in the state of California from grocery stores, but it's just a staggering number.
Yeah.
So I don't think they'll ever run out of that. Yeah. Yeah.
Can this kind of thing be scaled up to urban green wastes and other sources of organic?
Well, the problem with using other kinds of waste is that the waste will be degraded, right? So if you pick up grass clippings that are 10 days old, that's not the same as having fresh produce, and it's not that that's necessarily bad, but it would be inconsistent. So I think you'd run into problems maintaining the level of consistency that would be necessary for a product like that.
You mentioned looking at some of the additional products that are on the market that are supposed to boost soil microbiology in tandem with this, but have you looked at how this affects the soil microbiology?
No, we're actually starting to do that. So, in a very crude way, we're going to start looking at soil respiration measures to see if we get a big bump, which I suspect we will. Then, figuring out what's causing it is a whole different and much more complicated problem than that.
Do you think it's economically viable for growers to maintain their normal treatment at half the rate and then phase this material in? It seemed like some of the effects were not synergistic, but there was an additive effect.
On some of the crops, the best results were from the product alone. From other crops, the half and half kind of application turned out to be better. So I don't know, it might be on a crop-to-crop basis, but also you have to remember that these applications are done on a soil with a lot of history to it, right? So if they're putting on 200 pounds of nitrogen per acre, there's still a lot of nitrogen in that soil the next year. So I think that, doing these things 2 and 3 years in a row is going to be a really important thing, because there will be, structural and nutritional changes in the soil that happen in a time frame more than a season. Yeah.
2 questions. So I understand the NPK is like 1 to 3%
Yeah.
range. What is actually the total carbon in the liquid? That's one question. And the second one is, you mentioned enzymes. I'm assuming this is commercial, proteases, lipases, and so on and so on.
Yeah. The number for your first question, I don't have it.
Total carbon.
Yeah, I'd have to look it up. Do you know, Andy?
No, if you get your email address, I can send it.
Oh, sure. Yeah, and as far as the enzymes go, they buy them from Novozymes.
Okay.
So nothing exotic.
Well, the mechanics of application. So you've got 75 gallons per acre, and I've got 40 acres going here. I've got a bunch of gallons. Are you going to hook your tanker truck to the drip line, or how does it work?
It was done through injection of the drip line into the drip line. So usually what they do is they sell the material in these big 750 gallon totes, and with a there's a faucet on it, and they just inject it in. Yeah. Neil?
So just an outright question. You said you were surprised with the bump up in organic matter.
Yeah.
I guess you're adding organic material to the soil, and so I'm trying to understand why that was surprising to you.
Because you're not adding enough to account for it. There's got to be processes going along that are the amount of organic matter you're adding.
So it's much less. So the samples were taken in that region and details, et cetera. So it's just more than you're adding.
The bump in organic matter is more than the amount of organic matter you're adding.
Okay.
That's why it was a little surprising.
The other question I had was in your trials. So the alternative, or one alternative for a sustainable cycling, is actually compost, right? So
sure.
Are you considering, or have you tested it against compost addition to? Because there again, goals are organic matter addition, slow release nitrogen.
No, we haven't. But
it seems like that would be the other interesting.
Well, and I would think actually they'd be synergistic working together. And one of the things that we're doing in the lab right now is to look to see if adding this material to soil increases the rate of breakdown. We started using
Filter paper.
we started with filter paper, and we're kind of moving to tamale wrappers because it's kind of more natural. But basically, just putting it in a petri dish with soil that we treat or don't treat, and then weigh it before and weigh it after, and see how much degradation occurs, and if we can increase it with that. So you can imagine, speeding up the rate of composting by adding this material. You could also see treating at the end of the year when you till in all of the green stuff to increase degradation rate too. So there's a lot of things that could all work together that we haven't started yet. But I don't see it as a replacement for compost, because there's structural things that you get from compost that you can't get from liquid. So. Okay, thanks. I think we got to get on to the next slide.